Hello everyone. In this video I want to walk you quickly through the process of building a Huffman coding tree for the particular set of character frequencies that are shown in the lecture notes in this slide here, for example. We have a document with 6 characters, A through F, and with those particular frequencies, 9 A's, 8 B's, 15 C's, and so on, for a total of 42 characters, or some multiples of each of those. So to remind you, the problem is to construct an optimal binary prefix coding tree. So a binary prefix coding tree is one where the characters that you're trying to code up are the leaves of the tree, and the path from the root of the tree to any of the leaf nodes gives you the code sequence or the bit sequence for that particular character. So to encode a D we go 0, 1, to encode an E we go 1, 0, F 1, 1, and so on. So that's the problem, and Huffman coding is the optimal solution to that problem. So I'm going to begin by constructing the set of leaf nodes that we're going to have to shuffle around. So we need an A with a frequency of 9, we need a B with a frequency of 8, and I'm representing them with a comma like so, rather than with 2 separate labels as in the graph, as in the lecture notes, because in the lecture notes I have external labels and internal labels, and I don't have that capability in this tool. So I'm just using a comma so you can see which is the internal and which is the external. D is 3, E is 5, and F is 2. So there's the leaf nodes, and I'm going to have to somehow or other build a tree. The starting point for Huffman is to sort them into order of frequency, starting with the lowest. So F goes at that end, followed by D, followed by E, followed by B, A, and C. So there's the ordering. And you can think of this as a sorted list or a priority queue, really. And the algorithm works, as explained in this slide here, by repeatedly pulling out the 2 smallest nodes and building a tree from those. So just to demonstrate, I'm going to start here and construct a new parent node, which is going to have the combined frequency of those 2, which is going to be 5. It's also important to note this bit on the bottom of the slide here, that I have to put the lowest frequency node on the left, so 2 is less than 3, or if they're equal, I put the lowest character, the subtree, if necessary, that contains the smallest character on the left. So then I just have to build the 0, 1 edges, 0 and 1 like so. Missed, got it that time. You can nudge them with this tool to get it in a better place. And there's that has to be reinserted in the sorted list. So in this particular case it goes at the head, and we now have 5, 5, 8, 9, 15. They're sorted again. Same process again. By the way, this won't work for you if you try it in the normal code runner. I've got a special version here, and which allows me to drag whole subtrees. So I now connect that to a 0, that with a 1, and again give it a nudge because it looks better that way, and I have a new combined node of 10. That gets reinserted in the list, but of course it isn't in the right place now. It should be further over, so I have 8, 9, 10 and 15 like so. That's the sorted list. Repeat the process. 8 and 9 have to be combined to create a new node which has a combined frequency of 17. 8 plus 9, that's 17. Put the 0 arc in, the 1 arc in, and nudge it. Now we have 17, 10 and 15, so the order is completely wrong now. This one should be over there on the right. 10, 15, 17 like that. Just to repeat, I have a special capability for dragging whole trees in this particular version of the plugin. So carry on. 10 combines with 15 to create a node with a frequency of 25. Connect the nodes like so. That's the 0 and that's the 1. Now they're in the wrong order again. I have to put the 17 to the left and the 25 to the right. Let's put them down here and create a new node which has the combined frequencies of the 2 of them, and that should of course add up to the total number of characters in the document, which fortunately it does. 0 and 1. And that should be the answer, unless I've goofed. Let's quickly check. That should be this thing here. 0, 17, B, A, F, D, EC. Looks good. From that I can now read out the particular encodings for all the characters. So A has an encoding, there it is there. I have to go 0, 1 to get there, so that's the coding for A. B is here, I have to go 0, 0. C is somewhere down here, 1, 1, and so on. You can fill out the rest of those. If I then fill out that table of the characters and work out the frequencies or work out the number of bits to represent each character in the whole document, you'll see since I've got 2 bits per A and there's 9 of them, that gives me 18. I've got 2 bits for B, 8 of them, 16, and so on. And if I do that, it turns out I require 99 bits for the whole document, which has 42 characters in it, so I have 2.36 bits per character. And it turns out that's optimal because Huffman is always optimal, and if you want to read the proof, you can see there. You can look through these slides. There's just a few comments, first of all, on the order of complexity. I started with N items in the list. At each stage, I pulled 2 of them out. I combined them to create a new node, which I reinserted. Inserting into a priority queue is big O log n, so that's log n. I had to do it n times, so I have an n log n algorithm. To decode any particular sequence of bits in the an encoding, multi-character encoding, I start at the beginning, work down the tree from the top, 0, 1. That consumes the first 2 bits of the code message, and it gives me an A. I'm now starting again at 1, 1, 0. So I go 1, 0, have to keep going, 0, 1. That takes me down to D. So I've got A, D. Then I start again at that character and so on. You can work through the rest of them. You should get A, D, C, B for that simple coding sequence there. As explained on this particular slide, if you work through this process with a very unbalanced frequency distribution, 1, 2, 4, 8, 16, 32, which is nice and binary, as I'm sure you realize, you get a nice very binary sort of tree where it takes 1 bit to represent F, 2 bits to represent E, 3 bits to represent D, and so on, and that gives us that table there. It's worth noting that when you transmit a message using Huffman coding, you also have to send the coding alongside, so there's a bit of an overhead there, and it's not good for very short documents, of course. Or you can fix the coding tree to some known standard distribution, such as that of the English language. And there's the frequencies of all the letters in the English language. Just a few notes on Huffman generally. It is a globally optimum coding, but there are gotchas here. It's if the document's very large and the frequencies of particular characters changes during the document, there's no way of tracking that. You're only going on overall averages. So as a silly example, if you had half the document in English and half in French, you'll just have some sort of average coding. It doesn't recognize patterns, common words, for example. So THE, which occurs very frequently, is encoded with exactly the same number of bits as HET, which is a very rare word. Well, fairly rare. If you want to be really efficient, actually, nowadays you tend to use algorithms like Lempel-Ziv, I've misspelt it there, or LZW algorithm variants of that, which give much better compression because they are able to encode frequently occurring sequences like words or even whole sentences if they get repeated. And those are the algorithms that are used by familiar encoders like zip and gzip and so on. And that's it for Huffman coding. Thanks for watching. Bye.